Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, hi, I'm Andy Gordon. I'm from the Programming Principles and Tools group. So I've been inspired by the sort of area of probabilistic programming. We've been looking for the last few years at how we can apply programming language ideas in machine learning. And in particular, what we've come up with in collaboration with folks in the machine learning group here is this new probabilistic programming language called Tabular, which is intended to be something that can be easily embedded within spreadsheets in order to write graphical models directly in spreadsheets. Let's see, probabilistic programming so far has been aimed at sort of more or less at sort of machine learning experts, which is a reasonable place to start, actually. And Infer.net uses this form of C#, probabilistic C# that John was talking about, that surfaces within Visual Studio within a full-on development environment. And what we're trying to do in Tabular is go beyond that to the larger audience of people who are more comfortable in things like spreadsheets and ask what would a probabilistic programming language look like if it was embedded within spreadsheets. So probabilistic programming, a great many of you know about it, so I won't linger on this, but just to sort of fix some terminology. I mean, a probabilistic programming language is really starts from some other programming language and then adds some features so that we can represent things like graphical models, or more generally just define joint distributions over variables. So generally, we start with a particular programming language, like a functional language like Church, which is based on Scheme, or probabilistic C#, which is based on C#. You add some way to do random draws from distributions, such as coin flips or from Gaussians and so on. And we also had some way to constrain the execution of the program to actually condition it on observed data. So Infer.net has an observe statement, and there's a similar thing in Church. And then somehow you need to say which variables you want to infer, which is great. And it's much better than writing code for graphical models from scratch. I mean, that used to be the work of a PhD, and now you can sort of write a program in Infer.net or Church and get a reasonable and sometimes very performant inference algorithm from the compiler. And there's a bunch of systems out there. The granddaddy is Bugs, invented in Cambridge 20 years ago, which has inspired Stan from Gelman's group at Columbia, and there's a bunch of different languages. And the one that we're focused on is Infer.net. And we did a functional version of Infer.net using the F# system here to drive Infer.net. But that's not, and the Tabular language is a descendant from that, but it's a little different. Still, when you look at the actual graphical models that are the common graphical models anyway, they're really rather simple programs, and they don't need the full control structures that you have in languages like C#. So you maybe have loops, but very often they're just straight loops over a data structure akin to a map in functional programming terms, where you're generating a sort of, where the data structure is seen as being IID. And you often don't have complicated while statements with complicated conditions, and you don't have exception handling. There's a whole bunch of stuff you have in full-on programming languages that a professional programmer would know about that you don't actually need. So we asked ourselves, we're aiming at a large population of users who we could expect would know about relational schemas for their data. You can't do machine learning without data. So at the very least, if you're going to do machine learning, you have data in a database. So we could assume they know something about the schema of the data. And we said, well, what happens if we just take that as a sort of outline for our probabilistic programs and sort of mark up the schema with probabilistic expressions to define the model? And that's where Tabular comes from. So our intent is that new domain-specific language to help end users get insight from their data. And we're aiming, there's a kind of spectrum of users. I think everyone in this room is sort of on the right, machine learning PhDs. And we love machine learning PhDs, but maybe you're already well served with other tools. And then there's data scientists who are more sort of relatively sophisticated people. There's a reasonable number of them. And then there's machine learning developers, people who kind of, by accident or chance, they were developers anyway, and machine learning has become important, so they learned a bit. But they're people who are comfortable in things like Visual Studio or Eclipse. But then there's a really large group of people that Pat Hanrahan of Stanford calls data enthusiasts. These are sort of business people on a mission. This is like a doctor who wants to know why a certain class of patients keep on returning, or a car salesperson who wants to figure out, which cars are good to buy at auction and so forth. These kind of business-related questions. There's an awful lot of these people, and we feel they're comfortable in things like spreadsheets. So we want to see if we can take the benefits of graphical modeling and probabilistic languages to that population. So our principles: we want to design a language on the annotations of the schema. We want to, inference, deciding which variables to query. We're going to use a spreadsheet paradigm, and I'll illustrate that in the next few slides. And thirdly, we want to actually auto-suggest models based on the structure. And that is something we're not finished yet, but that's in progress. So we have a POPL paper. POPL is the ACM Principles of Programming Language Conference. And we had a paper about this last month at POPL, and it was about points 1 and 2. And 3, you might have seen work that Tora, I don't know if Tora's in the room at the moment, but Tora led some work called InfernoDB a couple of years ago, where he was automatically inferring graphical models from the structure of a relational database. And we've really designed Tabular to be able to write down those sorts of models, and I'll say a bit about that towards the end. Okay, so to introduce it, let's think about TrueSkill. And I'm assuming people broadly know the TrueSkill model. This is a sort of binary version of it, where you've got a population of users, and then you've got there's been matches, binary matches between them, and in each case, there's one winner. Okay, so the data might be here, that's your users, and then you've got a table here of matches. So this is saying that Alice meets Bob, and Alice loses, and then Bob meets Cynthia, and Bob loses. Okay. So then the schema for the data would look like this. So note we've transposed things, which often happens, so that the data sort of goes downwards, but over here, where we sort of transpose things, so the columns over there have become rows. All right, so my schema for the players table just says there's a name column that's a string, and the matches table has got player 1 and player 2 columns, these guys that are foreign keys over to the players table. Okay, they're indexes to the players table. And then there's a Boolean that says whether player 1 has won or not. So that would be the schema. So the idea is we can define TrueSkill by marking it up as follows. Okay, so this is an example of a tabular program. Okay, and it generates this graphical model up here. So the players table, we've augmented it with a skill. So as you remember in TrueSkill, the idea is that every player has got an unobserved skill. And the prior on it would be that it's a Gaussian, say, with mean 25. And this is the precision, so standard deviation 10. Okay? And what we've done is we've just added a new row to the schema, which is labeled as being latent, and colored gray. So the idea is that we're saying that this column doesn't exist in the real data set, but it's something we want to infer. Okay? And then on the matches table, we've added a couple of other latent columns for the performance. So if you remember in TrueSkill, the idea is that when two players meet, the winner is the one who doesn't have the highest skill, but the one who has the highest performance, where the performance is a noisy copy of the skills. So the two performances are noisy copies of the skills. So here we say player1.skill, which uses the player 1. In each row, it uses the player 1 field to get the skill, and then we add a bit of noise, and similarly for perf2, and then we just ask whether perf1 is greater than perf2. So notation, I'm sure you're probably more familiar with these notations. This is a sort of plate-style notation for this. And so you see that each of the columns in the database and also the latent columns have all become random variables in the factor graph, right, the circles. And we've got the color coding. So the blue ones are ones that are inputs, sort of covariates that we do not try and predict. And the orange ones are outputs, things that we're trying to predict. And then the gray ones are latent random variables. And then these factors, I've actually labeled these factors with the probabilistic expressions. Explicitly, the factors connect the random variables and describe a generative flow. And you see that each table over here has become a plate. So this plate here is iterating over all the players in this table, and this plate over here is iterating over all the matches. Okay, so you see there's a direct way of synthesizing these plates, these graphical models with plates from the shape of the schema. So then, what about querying? We have two styles. We have query by latent column, and then I'm going to have query by missing value. And the idea of query by latent column simply is that if we take a data set and a model, we can just infer from that data, by conditioning the model on it, what the columns are. So in the case of my example, you'd get these, that we'd fill in the skills as a new column and also the performances. And you're getting what you'd expect, that Cynthia's beaten Bob, who's beaten Alice, so you're getting the skill of Cynthia is probably larger than the skill of Alice. And then query by missing value, the idea is that in the output columns, the orange columns, we're going to allow missing values, okay, because we're predicting them. So here we say, all right, someone's offered me a bet on whether Cynthia is going to beat Alice or not. So what does the model think? How likely is it that she'll win? So we can just go ahead and fill in a probability observed from the model. So the idea here is we've got a very simple sort of interface that we've marked up the schema with the model, and then in order to do querying, we leave gaps in the output columns, and then Tabular can fill it in. So here's a slightly more complicated model that illustrates another feature, which is that we can also have variables, random variables that sit outside the plates. So that didn't happen in TrueSkill. But this is a very simple model of linear regression, where I've got A and B. So it's the equation, that Z is A times X plus B, and then the observed Y is a Gaussian of Z. So A and B are sort of static variables outside the plates, and they're given in this case these particular priors. So the corresponding factor graph looks like this, where A and B are variables sitting outside the plate, and they have these factors on them as a prior, and then this is a plate that takes each input X and produces an output Y. Okay, so that's pretty much all there is to at least the core form of Tabular. And so we have a particular recipe. The idea is we'd start with a schema, add latent columns, write models, and then we learn the columns and parameters, or we can use the query by missing value to predict missing values. And Tabular is meant to be sort of independent of particular ways in which you might visualize data, and it's also to some degree independent of the particular backend. So we're targeting Infer.net, of course, but we think it could also be. We're not really doing anything here on inference. So any benefits that John and Co add to Infer.net, hopefully Tabular would inherit. But equally, we could also target other backends. So in Bangalore and MSR, there's a sampling-based backend being developed for Infer.net, and we'd aim to target that also. And so we can. So this is a screenshot of this embedded inside Excel. This is actually done by Danny. So he was our first user. So it's great to have a user, but he's an ML PhD, so he's a little bit on the high end for us, but it's great. We're looking to start with some users. So this is a variation. I'm not going to try and explain this, but it's just to give you an idea of what it would look like in Excel, where you'd have your data in these leagues, teams, and games tabs here. Here is your model. We can actually auto-generate a model that's sort of completely empty with, or maybe has some default modeling expressions in it from the schema, and then the user can edit them, and we do syntax checking and syntax highlighting and so forth. You see there, and then you see there's the results being dropped into the sheet, and then we just use the visualization features of Excel to do a plot. Okay, we wanted to show in the paper, we want to compare it to the best available alternative, which is directly doing a model in Infer.net. So we took a model already been done. It was complete before we started. It was led by Joran Bachrach and others. John Guyver was involved in that. And he'd written this C#, so this is sort of like best practice C# model in Infer.net. And this is the equivalent thing in Tabular. And we ran some numbers, but the harder thing is we get the same answers. So statistically, these numbers are this. So each of these, so this is 3 different models, right? And the 2 rows here are Tabular versus directly doing it using the current Infer.net API, and then the same for another model, and the same for a third model. And you see these numbers are all the same. So we get the same answers. We've got a few lines of code as expected, and performance-wise of inference, where we take a little hit, but only a percentage or 2. So it seems entirely viable to go this way. Do consider downloading the paper. It's in a programming language style. But I have to tell you, we worked really hard to make this paper accessible to a machine learning audience. Danny gave us a lot of useful feedback. There was a lot of iteration on it. So I think you'd find, even if you don't have any background in programming languages, give it a shot. I think the first few pages are pretty readable, and it gives you an idea of how you would explain, Tabular. Here's the full syntax. We have various theorems. I'm standing between you and coffee. I think I officially have 5 minutes. I'll try to get this finished in another 5 minutes. So there's various theorems, but what I really want to say is automatic model suggestion. So this is our current work, And maybe this is related to some of the work Zubin and others of you have been doing on the automated statistician. So this is, if you may have seen the work that Tora did with an intern, Samir Singh, a couple of years ago. The idea was you'd start from a relational schema and generate a model. And in this case, it's like a user movie recommender, where you've got a table of users with some demographics, a table of movies with some features, and then you've got some ratings, where for each row in the ratings table, you've got a user ID, a movie ID, and a score. And they came up with this model. They came up with an algorithm for generating models, and they coded this up in Visio, this particular model. And in a way, a challenge for Tabular from the start was like, what does this mean? How can we describe this? You know, it seems this is kind of getting kind of hard to write down. You know, if I witnessed Samir and Tora in a bitter argument about the right notation, and we thought, you know, this is a nice programming language question, actually. You know, what sort of notation would naturally let you write down models like that? So I'll just quickly go through that. So let's start with this. That what the model does is that for the users table, let's see, it adds a cluster variable. So essentially, it clusters the users, it clusters the movies, and then uses the clusters here to predict the scores. And the way we could write this in Tabular is like that, where we have a new latent column called the user cluster that has a discrete distribution, and there's 4 possibilities. And then the gender and the age have conjugate Bernoulli distributions on them. So they've got a prior that's a beta in that case, and in this case, a Dirichlet prior, sort of outside the loop. But they're not a single one. The point is they're indexed by the user cluster. So we have this syntax here which says that so there's 4 different user clusters. So what this says is make 4 different parameters for this conjugate Bernoulli distribution. And then depending on, and in any row, depending on what the user cluster is, use the appropriate parameter. Okay, so it's a nice compact description notation. And similarly for the movie cluster, for the movies, you know, statically we are outside the table. We have in each row we have we do a draw of the cluster and then use that to index the models for the genre and the year. And then finally, when we predict the ratings, in any row we have a user ID and a movie, and we look up the cluster of the user and the cluster of the movie and use the pair of them to index a distribution over ratings. So for example, you know, there'd be a different distribution for when, say, an old female sees an action movie versus, say, I don't know, a young man sees an action movie, for instance. That's the kind of intuition. So that's it. That's all I have. We have the paper. You can get it on the web. Remember, researchmicrosoft.com/fun. We try and keep the fun in computing. Go there. There's various papers, including a full talk about this, and also, other papers. And I'm very interested to discuss more. Thank you.